In this video, we move on to Chapter 8, which is on comparative static analysis of general function models. It is important to note that we will only be briefly looking at this chapter, and only section 1.8 and 8.4 will be covered. Section 8.1 is on differentials. What's the difference between differentials and derivatives? For the derivatives, we are interested if the change in x becomes very small. For differentials, this does not necessarily hold. So from our previous chapter, we know that the derivative dy dx is equal to the slope f prime x, and that is equal to the limit as the change in x becomes smaller and smaller, approaches 0, of the change in y over the change in x. If we don't necessarily want this very small change, we have that our change in y over the change in x is equal to the derivative plus some change. If we rearrange this, the change in y over the change in x minus dy dx will be some change in x. So from before, we know that this delta is equal to 0 if the change in x will be equal to 0. If we take this function again and we multiply by the change in x, we have delta y equal to dy dx times the change in x plus some additional change. This is equal to f prime of x times the change in x plus this delta of x. This f prime of x can then be reinterpreted as the factor of proportionality between the two finite changes in dy and dx. Okay. An important application of total derivatives is elasticity. We know that the elasticity is equal to the ratio of the change in quantity given a change in price. So if we rearrange this, we have the change in quantity over the change in price times price over quantity. This is our marginal function or our partial differential, and this will be our average function. So if we have the quantity demanded equal to 100 minus 2p, the elasticity for demand will be equal to the derivative of q with regards to p, which is minus 2, multiplied by P over Q so we know that Q over P is equal to 100 minus 2P over P. So P over Q will be equal to P over 100 minus 2P. So this will be equal to minus 2 times P over 100 minus 2P, which is equal to minus 2p over 100 minus 2p, and that is equal to minus p over 50 minus p if you factor out a multiple of 2. Then we have section 8.4, which is on total derivatives. Total derivatives is if we have a function y, which is dependent on x and w, but we have a new function where x is dependent on w. To get the total derivative, y will change if x changes, but x will change if w changes. This happens via the function f. This happens through the function g, but we also have a direct impact of w on y with the function f. So if we want dy dw, we need this partial derivative, dy dx and dx dw plus this partial derivative dy dw. That is the same as the slope fx dx dw plus the partial derivative dy dw. If we multiply through with dw, we are left with f of x dx plus f of w dw. So let's do an example. Y is equal to a function of x and w, which is equal to 3x minus w squared, and x is g of w, which is equal to 2w squared plus w plus 4. dy dw is equal to dy dx dw plus the partial derivative dy dw. dy dx is equal to 3. The x dw is this function's derivative, which is 4w plus 1, plus the partial derivative dy dw is minus 2w. If we simplify, we end up with 10w plus 3. Alternatively, we could replace x with 2w squared plus w plus 4 in this first function, simplify, and then take the derivative. You will end up with the same answer, but with additional steps. Another example is if we have a production function. So our production Q is a function of capital, labor, and time, but our capital is determined by our capital stock over time and labor by our labor stock over time. So how would we know how our production changes over time? So we would first have dq dk. So how does production change with capital? But capital is determined by time, so times dk dt. Our production changes with labor, but labor changes with time, and there is some independent partial function that time changes quantity as well.